Hello everyone. In this lecture, I'll be talking about array-oriented programming with arrays with focus on mathematical and statistical methods. We also briefly talk about the simulation of random walk, which is a great application of utilizing arrays operations. We will have a preview of Matplotlib library that we use for visualizations as well. So here you see a new method named MeshGrid. Under numerical Python package, MeshGrid takes two one-dimensional arrays and produces two two-dimensional matrices, which correspond to all pairs of x and y in these two arrays. And here you can see an example. We import two libraries, numerical Python and random, and then we use the arrange method to generate 1,000 equally spaced points starting from -5 to 5, and the start value is 0.01, so 1,000 data points. And then we apply the MeshGrid to points. So this point is an array. Okay. So we pass points, which is a one-dimensional array, to this function, and the result would be two matrices. We call one XS, the other one YS. So when we run this in a notebook, you're going to see what it looks like, but it takes into account all possible pairs of X and Y in the first and second arrays. And then we can apply a function. In this example, we are calculating the square root of this term. First, we raise all elements in XS to 2, and then we do the same for YS, and then we add them up. So that's the function that we define, and you can see that we can do arithmetic operations easily, and then we pass it to the sqrt function. And then we import Matplotlib library. This is the main library that we are going to use for visualizations. So matplotlib.pyplot, you can see it's a long term. So we assign a nickname PLT, which is a short version, and this PLT refers to Matplotlib library. And in this example, I'm using IMShow to show the results of the Z value. So I pass Z, and then CMap as the color map. Here we go with the grayscale, and we also want to see the color bar. So let me implement this in Python, and you can see the result for the MeshGrid method, how we can apply a function just in one line of code, and then visualize the results. So first I create a one-dimensional array using the array method, using the arrange method, which is array range between -5 and 5 as the value 0.01. So let's run this. If you print, so you can see all values, it's too many data points. And if you want to check the shape, so point.shape, then you can see how many data points you have, which is 1,000, a one-dimensional array. Now we can apply MeshGrid to generate two matrices using this array. So we call XS and XY, so YS, np.meshgrid, and then we pass points. We need to pass two one-dimensional arrays, and in this case they are the same, the points array that we just generated. And let's look at XS, for example. So from -5 and all other possible points, so -4.999 and so on. So if we apply the shape, just to see the shape of this matrix, you can see now you have 1,000 by 1,000 matrix. It's the same for YS matrix. So it starts from -5, -5, and all possible pairs. And if you apply shape, you can see that it's 1,000 by another 1,000 by 1,000 matrix. Then we can apply any function that we want to all elements of this matrix. So let's define another variable named z. NP, let's say we want to calculate the square root of all elements in the matrix, but first we raise all elements to 2, so x is raised to 2. The same for ys raised to 2, and then we add them up. Then we apply the square root. So let's print z. You can see that it's an array, and if you look at its shape, then it's a matrix, 1,000 by 1,000 matrix. So in this example, we learned about mesh grid and how we can apply functions to all elements in that matrix. Now we want to visualize it. To visualize the result, to plot data points, we need to import a new library named matplotlib.pyplot, and we are going to talk about this library in details later on. I assign a nickname plt. Then under plt we use the imshow function, which creates an image plot from a two-dimensional array. So we need to pass a two-dimensional array, here z, which is a matrix. Then the color map, the keyword is cmap. It's under plt, cm, color map, and then gray. So it will be the gray scale. Also, we want to see the color bar because it's like an image. So plt dot color bar. And now let me run this, and this is the result. So technically, this is the square root, this is the function, and this is the square root of x raised to 2 plus y raised to 2. So you can see something like circle in the middle. And it's a gray scale, and you can see the color bar, and that's just a preview that how we can visualize the result. Now, under mathematical and statistical method, we can use aggregations like sum, mean, and a standard, either by a standard deviation or variance, either by calling the array instance method or using top-level numerical Python functions. So in this example, first we generate a matrix, a random matrix, and here np.random, I'm using rand_n. This is a new method or function. We generate random number from a standard normal distribution. And then the size is 4. It means 5 rows, 4 columns. Then you can apply the mean method, and then it calculates the mean or the average of all items in the matrix. The same for sum. Now, if you pass access, then you can control you want the mean across the column or down the rows. So if access is equal to 1, then it computes mean or sum across the columns. And if access is equal to 0, then it computes mean down the rows. And you're going to see the example here. So let's run this. When you see the numbers, it makes better sense. So let's generate a random matrix, np.random.rand_n. So rand_n is the new function which generates random numbers from a standard normal distribution. The size is 5 by 4. Let's run this. When we print it, then you can see it has 5 rows and 4 columns. Then we can apply mean function, then it returns one value, which is the average of all items in this matrix. You can also apply other aggregations like sum, so it add up all elements. Now if you pass access, so let's say we go with mean, and then access is equal to 1. Let me add the comment here. So it means that it computes mean across the column. So let's run this, and then you can see an array 1 2 3 4 5, because you have 5 rows here, so you see one value for each row. Now if access is equal to 0, then we see 4 values. A dot mean, because we have 4 columns. And this one compute mean down the rows. There is a typo. So you see 1 2 3 4 items in an array. So we can calculate the standard deviation or variance, and I'm going to show some common functions that you can apply to arrays in the next slide. But before we talk about other functions, I would like to point out that numerical Python arrays can be sorted with the sort method as well. In this example, we generate a random one-dimensional array. So I'm using rand_n, standard normal distribution, 6 items, and then we apply sort. So let's see what the results look like. np.random.rand_n, size of 6. So it's a one-dimensional array with 6 elements. And if you apply the sort method, and then if you print B, you can see that all elements are sorted in ascending order. Negative value 0.16, then 0.59, 0.69, and so on. So by default, it sorts in ascending order. Now here I would like to discuss one example, useful example of sorting elements in an array. A quick and dirty way to compute the quantiles of an array is to sort it first and select the values at a particular rank. So if you want 5% quantile, 10% quantile, so what we do, first we apply the sort method, and then we can simply calculate different percentage of quantile. In this example, we are calculating 5% quantile for a randomly generated array using rand_n. We have 1,000 items, we sort them, and then 0.05 times the length of that array returns the 5% quantile. So let's see what it looks like. First, I define a variable named c np.random rand_n. We want to generate 1,000 elements. Let's apply shape. So you can see there are 1,000 data points. We sort them. C.sort. And now we can calculate 5% quantile. First off, it's integer 0.05, because it's 5%, times the len, which returns the number of elements in C, and you can see this number. So let me add the comment. This is 5% quantile. If you want to calculate 10%, then we have 0.1 times len of C, and then you can see the 10% quantile. So that's one useful application of applying sort method to arrays. And here you can see basic array statistical methods that you can apply with one line of code. Sum returns sum of all elements in your matrix or your array. Mean returns the arithmetic mean or average. STD and variance calculate a standard deviation or variance. Argmin and argmax, it returns indices of minimum and maximum elements in your array. Cum returns cumulative sum of elements that we are going to use that in our random walk simulation. And the last one returns cumulative product of elements starting from 1. Now that we learned we can apply some mathematical and statistical functions to arrays, let's talk about one of the useful applications of arrays operation. Random walk is a stochastic and random process. It describes a path consisting of a succession of random steps on some mathematical space, such as integers. A simple example of a random walk is the random walk on the integer number line. So it starts at 0, and at each step it moves one step forward or one step backward. In other words, it moves +1 or -1 with equal probability. You can think about flipping a coin. If it is head, then we move +1 or one step forward. If it is tail, then we move -1 or one step backward. In this example, you can see the simulation of random walk. And here we are using list as the data structure. We use the random module. We define a variable named position equal to 0, so it shows the origin of this process. And then we define a list named walk, and the very first element is the position, which is 0. And in this example, we want to simulate 1,000 steps. So I define a variable named steps equal to 1,000. Then we write a for loop. So for I in range 1,000, so 1,000 times we want to repeat this process. A step is either 1 or -1. So if random.randint is positive, then it's 1. Otherwise, if it's greater than 0, it's 1. Otherwise, it's -1. So let's look at this randint. Randint between 0 and 1 returns either 0 or 1. So with this condition, we are saying that if it is 1, then a step is equal to 1. Otherwise, it's -1. So we move one step backward. And then we have the augmented assignment. Position is equal to position plus a step. And then we use the append method to populate that list, so the sequence of items. And eventually, when we have a list with 1,000 items, then we can plot it. And in this example, we use the matplot library, the plot function, and we just visualize the first 100 values on each of these random walks. And that's what you say, colon 100. Now let me implement this in a notebook. We plot it, and then you can see the result for the random walk. So we import random. We define the origin of the process, position equal to 0. We define a list walk which starts from position, which is 0 in this example. Then we want to simulate this process for 1,000 times, so a step equal to 1,000. Now we have that for loop for I in range steps. Okay. A step is equal to 1 if random.randInt between 0 and 1 is greater than 0. It means that when it is 1, a step is equal to 1. Otherwise, it's -1. So you can see it's another format of defining the condition. Or you can define if statement first, and under the condition, you add a step, or you go with this format. Either way works fine. Then we have the augmented assignment position plus equal a step, and then we populate, save everything in that list, the walk.append. So we add the positions. So let me run this. There is a typo here. Okay. Now let's print walk so you can see the values. Some are negative, positive, and you have 1,000 data points. So if we apply shape to walk, then it returns. Okay, here's the thing. So this is the list. So if you want to know the size, we cannot apply the shapes. Shape is applied to arrays, right? So far we didn't use any arrays operation, but we could simulate the result. So keep this in mind that shape doesn't apply to list. Instead, we want to plot this and change the process so we can apply shape. So technically we want to change the data structure to arrays, and you can see how simply we can simulate the same process and plot the result. But let me plot the result based on this list. So I apply the plot function. We just plot the first 100 values, and then this is the result. So first we started from position 0, all negative, and then we go up again with a step backward, and you can see that the randomness in this process. If you want to see the first 200 results, then this would be the result. And if we want to plot all instances, 1,000 steps, this would be the result. Now, if we take a closer look here, we can change this to arrays and apply array operations. So walk is simply the cumulative sum of the random steps and could be evaluated as an array expression. So here we use the random module to draw 1,000 coin flips at once, and then set these to +1 and -1 and compute the cumulative sum. We just talk about the functions that we can apply, and you are going to see 3 of them in this example. So first, number of a step, a variable, it's 1,000, and then we generate 1,000 outcomes for flipping coins. NP random, randInt, between 0 and 2, and the size is equal to n steps. And here we can define conditions for arrays using the var keyword. So step is equal to numerical python.var. So this is the first time we are using var to an array. So np.var if draws is greater than 0, then step is equal to 1. Otherwise, it's equal to -1. So when we are using the var statement, the first argument is the condition. The second argument is a true value. So if the condition holds, then the variable is the second item. If the condition doesn't hold, then we pass the third argument. Then we apply the cumulative sum function to steps, which is an array. And then when we create that walk, remember, if we apply the min function to walk, when walk is a list, we cannot, we get error. But now that walk is an array, then we can apply min and max functions. We can also define more complicated statistics based on the combination of functions that we just learned. In this example, let's say a more complicated statistic is to know how long it took the random walk to get at least 10 steps away from the origin 0 in either direction. So it can be +10 or -10. So I define the condition numerical python dot absolute value, because either condition is acceptable, +10 or -1. So the absolute value of walk equal or greater than 10. So this condition returns a Boolean array, indicating that the walk has reached or exceeded 10. But we want to know the index of the first +10 or -10. Then we apply the argument max method, which returns the first index of the maximum value. So let me implement this and you can see the result. Here walk is a list, so if I want to find the minimum value, I need to write a for loop, right? So let me apply min here and you can see it throws an error because list object has no attribute min. But we change this to arrays. So n step, 1,000 steps for this process, and then we define a draws, which is an array, but we use the random and rand int function between 0 to and the steps, so we or the size. So we generate 1,000 outcomes at once. So let me run this, and if you look at draws, then you can see that it's an array. The outcome are 0, 1, because we have the rand int. And if we run it, you get another result because it's a random process. And then now we can apply the shape. So draws.shape, you can see that it's 1,000 elements. And now we can define the condition, right? Steps is a variable, is an array. We use the var method, so we define the condition. If draws is greater than 0, it means that when it is 1, we pass 1 to steps. Otherwise, we pass -1, just with one line of code. And let's look at steps. So we only see +1 or -1. And if we apply the shape method, you can see there are 1,000 elements. Now, if we add them up, so we apply the cumulative sum to steps, then it's the same as the walk variable. So walk is steps dot cumulative sum and then you can see the result. So it's another array which represents the walk variable based on the outcome of a step. Now I can find the minimum value because we simulated this process for 1,000 steps. Then the minimum value was -5 in this experiment. We can also find the maximum value, which is 30. We can also plot the result for this one. Now this is the random process. Now the more complicated statistics that we want to know how long it took the random walk to get at least 10 steps. So now we can define that function. So np dot absolute value ABS of walk variable greater than 10 greater or equal to 10, and then we apply the argument max, the index of the first 10 or -10. If we run this, we can see it took 173 steps to move forward 10 steps. So in this example, we could simulate the random walks process using arrays. Then we applied some aggregation functions and other functions, and we work on a little bit more complicated statistic to find the maximum value or the first index of the maximum value. Now I move on to Appendix A. So in our second textbook, Appendix A discuss about advanced numerical Python package. And here you can see most commonly used method under advanced array manipulation. One is reshaping. So you can reshape arrays. It means that you can convert an array from one shape to another without copying any data. In this example, we are using the arrange method. We generate an array, one-dimensional array with 8 elements, and then we use the reshape method. We want to make it a 4x2 matrix, and you just pass 4 and 2. A multi-dimensional array can be reshaped as well, so it works for one-dimensional array and matrices. And in this example, first we reshape A and we change it to 4x2, and again we apply the reshape, and then we get 2x4 format. Let's implement this and you can see the result. So we first generate a one-dimensional array using arrange function with 8 elements. And now we apply the reshape method. So let's say we want 4 rows, 2 columns. And then here you can see that the array is reshaped. We have 4 rows and 2 columns. And also we can apply it to multi-dimensional arrays. Let's say a.reshape 4x2. We apply reshape again and change it to 2x4. If we run, you eventually see a matrix with 2 rows and 4 columns. Another useful method is flatten. The opposite operation of reshape from one-dimensional to a higher dimension is typically known as flattening. It means that it collapses all elements into one single array. So let's say we use the arrange function with 15 elements, and then we reshape it. Now it becomes 5 rows and 3 columns, and then we apply flatten. Let's see the result in the notebook. So B is np.arrange with 15 elements, then we reshape it 5 by 3, so 5 rows, 3 columns, and now we apply flatten method. So you can see it becomes like the original array, which is the arrange of 15. So one-dimensional array is starting from 0 through 14. Another useful method is repeat. We can repeat elements. So we can apply repeat to the matrix B we just generated, and then you pass 2. It means that each element in that matrix or array will be repeated 2 times. If you pass 3, then each element will be repeated 3 times. So B here is this array, then B dot repeat, let's pass 2. Then you can see 0 is repeated twice, 1 twice, the same for all elements. And with that, I conclude this lecture.